welcome back to my channel, and today we're going to be learning about sets. Sets may seem complicated at first, but I assure you, they're very easy. So, before we dive straight into sets, I want you to hit that subscribe button, hit the like button, and ring that notification bell. It really means a lot to me, and plus, you'll be getting notifications on new great videos every day. So, I'll see you in another video after this. This will be a nice series, and on the last episode, I'm going to ask you some questions to review your knowledge. But first, let's get to the basics. Types of sets. Sets are normally written in curly brackets like this. If you want to list anything inside a set, we use these brackets. Numbers and values inside the set are normally called elements. For example, if we have A is equal to 1, 2, 3, we can say that the set A has 3 elements, 1, 2, and 3. There are 2 types of sets, which are roster sets and builder sets. We're going to go and look at more types of sets as well, but let's start with these 2. Roster sets. Roster sets are sets that have only the elements in them and are normally the most common sets you'll ever see. Here are some examples. A is equal to 1, 2, 3, 4, 5, 6. B is equal to yellow, orange, red, blue. C is equal to 3, 11, 9, 6, 5. And D is equal to A, B, C, D, E, F, G, H, I, J, K, L. And so on. Elements can be anything here. It's just a value. It could be colors, like objects in a sport. It depends on the question. It can be numbers. It's mostly numbers in maths questions, but it could be anything. It could be letters in the alphabet. And another thing, basically a roster set is a set which has elements inside it. So you and me, we could already list a lot of roster sets on this page. But these 4 are just here to give you an idea. Just remember, these are not all of them. There's an infinite amount of roster sets. And that's the same for the next type as well. Builder sets. Now, builder sets don't have elements in them, but they have the properties of the elements inside them. You could say that the generalized form of the builder sets is this. A is equal to, curly brackets, x colon property. Where it says property is where you put the properties, but the rest will be the same. You always must define x and talk about its limits in the property. For example, if A is equal to 1, 2, 3, 4, then in builder form, A is equal to x colon, x belongs to n, and 1 is smaller than or equal to n, which is smaller than or equal to 4. If B is equal to 3, 4, 5, 6, then A is equal to x colon, x is equal to n plus 2, which means we simplify x into n plus 2. And then we say n belongs to natural numbers, and 1 is smaller than or equal to n, which is smaller than or equal to 4. If this may sound a bit confusing, you can go back through the video and listen to that again. But to make it easier, this E, the circular E sign, means belongs to. And the N, it means natural numbers, as shown here. Because the numbers in a set truly do matter. You can learn something about a set if you look at the letter on the left-hand side of the set equation. Here's a note. It's not always on the left-hand side. It can be anywhere. But if you see these symbols, that's what it means. But sometimes it could also just be the name of the set. But this is normally what it means here. N is a set of natural numbers. Z is a set of integers. Q is a set of rational numbers. R is a set of real numbers, and Z plus, with a little positive sign on the top, is a set of positive integers. The order of a set. The order of a set is the number of elements that a set has. The order of a set is also called its cardinality, or the size of a set. There is no such thing as a maximum or minimum cardinality. since we have a finite set which has a limit to an infinite set which never ends. Basically, the order is the amount of elements a set has, as it says here, also called cardinality or the size of a set. And as of the maximum minimum cardinality, what I mean is that for example, take the set of natural numbers. It goes 1, 2, 3, 4, and then it goes on forever. It never ends. So that's an infinite set. So that's not really a maximum cardinality. You couldn't call that maximum cardinality because it never ends here. And a minimum cardinality, you can have any minimum cardinality. You can stop here and stop here and stop here. So technically, there is no such thing as a maximum or minimum cardinality. You can't really say that. It will never appear in any type of questions. But as of now, the only thing you have to remember is that the order of a set is the number of elements that a set has, also called cardinality or the size of a set. Here's more types of sets. Empty sets. These are sets with no elements inside them. So here the example, A is equal to, you only see 2 curly brackets. There's nothing inside it. If there's nothing inside it, you can consider it an empty set. Empty sets are also called null sets. And null sets are also called phi. Phi is the Greek letter phi. It'll be in the PowerPoint later. But we can move on to the next one now. Singleton sets. These are sets with only one element different from the rest of the elements. For example, if we take B, it will be equal to 1, 2, 2, 2, 2. Here there's more 2's. The common element is 2, but you have just 1, 1. Which means that the one odd one out, you could say the odd one out element here is 1, while the rest of the elements are 2. So that's a singleton set. That's basically what it is. Finite sets. Finite sets are sets which have a limit to them. Example, C is equal to 3, 6, 7, 11, 19. So it's a set which has a limit, as we said before in the order, the cardinality. And we also said that infinite sets are sets that are never ending, have no limit, like a set of natural numbers as shown here. And there's also a set of integers, and it could be anything. And normally the set of natural numbers and set of integers, or anything that shows what the set is, like here, the n here, it may look fancy sometimes, but to help you show what it actually is, but sometimes it's also written as n, so you have to look out for that. Equivalent sets. Equivalent sets are the sets that have the same number of elements inside them. This means that the number only matters, not what the values are. Here's an example. We have A, 1, 2, 3, 4, 5, and B is A, B, C, D, E. There's 5 elements in each set. That's all that matters. That means they're equivalent sets, not equal, equivalent. Basically, the amount of elements inside them are equivalent. You could say that. And if you want to write it in a linear form, then we can say NA is equal to NB. This is not multiplication. The N with the brackets here only shows number of. The N here represents the number of elements in the set. Meanwhile, we actually have equal sets. For two sets to be considered as equal sets, all the elements must be the same. However, the order in which elements are in can vary. By the order here, we don't mean the cardinality. We mean the actual order, the order in which things are placed in. The order in which these elements are placed in. For example, if we have A is equal to 7, 6, 4, 2, 1 and B is equal to 1, 6, 4, 2, 7, which is basically A but written backwards, then A is equal to B. The order doesn't matter, it just matters that the elements are the same. Everything has to be the same except for the order of the elements. Again, not the cardinality, the order in which they are placed in. Then we can write A is equal to B. We don't have to write any denotation here because they're equal sets. We can just write the equal sign between both of them and we can say A is equal to B. Meanwhile, we have subsets. If all the elements in set A are in set B, then set A is considered to be a subset of set B. It also may be that there are more elements in set B than in set A. For example, if A is equal to 2653 and B is equal to 357286, then A is a subset of B. Here's a C with a dash, and it means a subset of, and also a okay, sorry. And here, to just explain what a subset is, here we have A is equal to 2653. 2, 6, 5, and 3 are the elements of A. And B, you can see, but they're in a random order, 2, 6, 5, 3. They're all inside the B, which means that A has to be a subset of B. It's that simple. And the order doesn't matter in here. The cardinality order doesn't matter. The order of the elements doesn't matter. It just matters that all the elements in set A all the elements of set A are in the elements of set B. Also, a subset of set B could be its equal set. For example, if C is equal to 357286 and B is equal to 357286, same sets here, then C is a subset of B. Doesn't really matter if they're equal sets. They just have to be subsets here. And finally, a null or empty set can also be considered as a subset to any set. This may sound complicated, but it's easy. If D is equal to a null set, we can say D is a null, and B is 357286, then D belongs to B. Because technically, if you take out all the elements in B, you are left with nothing. That's technically a null set. So basically, a D is a subset of B. Now we have supersets. Supersets are technically the opposite of subsets. Instead of being a part of the other set is a part of them. For example, if A is equal to 37452 and B is equal to 357, then A is a superset of B. The symbol here, which is the mirror image of a C, means superset of. So here, it's the same thing, just backwards. We have B is 357 and A is 37452. We can also say B is a subset of A. So it's basically going backwards now. A has all the elements of B, so A is a superset of B. So we can also say that any set except for an empty set is a superset of an empty set. May sound confusing, but yes. For example, if A is equal to 37452 and C is a null set, then A is a superset of C. Actually, a null set can be a superset of a null set because the final rule is, like in subsets, a set can be a superset of itself. For example, if A is equal to 37452 and D is equal to 37452, then A is a superset of D. So you can actually also say that a null set is a superset of itself. Any set is a superset of itself. Now, if it's starting to sound complicated to you, then you can go back in the video and you can see you can look at everything we've seen so far. But let's move on now, if you understand everything. Now we have proper subsets, which are the same thing as subsets, but now they're actually proper. Proper subsets are subsets, but we exclude subsets that are the set itself and subsets that are empty sets. For example, if A is equal to 39246, B is 326, which is a subset of A as well. C is a subset of A, but it's null. D is also a subset of A, but it's the same exact set. So we wouldn't say C and D are a proper subset of A, because one is null, the other is the exact same set. It's an equal set. So basically, the sets which actually have not all of the elements that A has, but not none of the elements. B here, 3, 2, 6. Perfect example of a proper set. 3, 2, and 6 are inside A. So we can say B is a proper subset of A, C is not a proper subset of A, and D is not a proper subset of A. Here the C, it means proper subset of. You can see the C here. It has no dash. or below it. So you can say C is a proper subset, and C with a slash over it is not a proper subset of. Now this basically means that any subset that has the same elements of A, but not all of them, and is not considered an empty set will be considered as a proper subset. This is the end of the first episode of sets. If you want to go back and look at everything we've learned, I encourage you to do so. And I shall see you on another episode where we'll be covering this next topic, operations of sets. So, I'll see you there. And before we go, I just would like to remind you to please hit that like button, hit the subscribe button, and ring the notification bell so you can see more videos like this. And I would really appreciate it if you do. So, please consider doing that. And I'll see you in the next episode. And the next episode in this series of sets. Goodbye!